Hi, everyone. I'm from the Lita Foundation. We'll be talking about the Valida VM and how we're using it to push the performance and usability of zero-knowledge proofs. Where's the slide advance? Okay. There we go. We'll be talking about ZKVM, zero-knowledge virtual machines, some of the different high-level approaches to designing these, as well as limitations with some of the other VMs on the market today, and some of the choices that we've made with Valida to get what we believe to be the fastest VM, as well as a little bit about the future. These last 2 points we probably won't get to here, but if you come to my ZK Accelerate talk tomorrow afternoon, we'll get a little bit more into the demos and benchmarks. So we've been talking about zero-knowledge all day, but let's recall a zero-knowledge virtual machine, it's supposed to be a universal ZK circuit. So something that allows you to verify the result of an arbitrary computer program. The desiderata, as usual, we want proofs to be succinct, much easier to verify than the original computation is to perform, and we want to do it in zero-knowledge, so not revealing anything about intermediate states or private inputs. As with much of ZK, the main difficulties with adopting this more widely today are the learning curve of the tooling, the high level of technical content required, as well as the proof systems themselves, their high energy, space, and time costs. So the first question that you ask when thinking about what is a ZKVM is, what does it mean to specify a computer program? Just about anything can simulate universal computation, ranging from ordinary programming languages to something like Magic the Gathering. So one approach here, and this is what we see in some VMs like Cairo, is to use a domain-specific language. So this is something where the interface looks something like a regular programming language, but you can think of it as a set of macros for generating circuit constraints directly. On the opposite end of the spectrum, we could have something that takes a high-level description of a program in a common language and directly produces an equivalent circuit. This is challenging to do, requiring a lot of sophisticated compiler tooling, as well as the usual high versus low-level trade-off, where high-level things are easy to reason about correctness, whereas low-level things are easier to verify performance, or reason about performance. So we take a hybrid approach where we have an intermediate representation of the program that is thought of as a set of machine instructions for a virtual machine. So much like actual physical processors. So we hope that VMs will be the main way in which developers interact with zero-knowledge in the future, avoiding the need for long learning times of ZK systems, knowledge of cryptography, as well as the potential security implications of working with these things directly. So some of the limitations with the VMs that are out there today are that the domain-specific language-based VMs can be difficult to work with, requiring developers to learn a specific language for the given VM, not being able to reuse code across different proof systems, and just representing a different way of thinking about programming than developers are likely used to. As well, some of the VMs on the market today do not have full open source support for all parts of the stack, by which we mean not just the core components of the verifier and prover, but including things like proof aggregation, proof recursion, and constraint generation. So many of the other systems around have some of these, but not all of them open source. As well, we want to have something like Ethereum precompiles. We want to have special hand-rolled circuits for common cryptographic operations, like signatures or EVM transactions, that can work faster than the equivalent bytecode. There's also inefficiencies in performance. Some of the things that lead to this are VM design issues where your memory model or your instruction set are not optimized for friendliness of representing in snarks, but rather for similarity to electronic computers. Another thing that we care about a lot is we want to be able to quickly integrate the zoo of recent cryptographic advances in this field. I think there's a new paper that kind of changes everything every 2 weeks at this point. One big thing here is support for small fields. As we've seen in the last year or two, this is really driving a lot of the performance gains in zero knowledge. So in other words, we need a VM that is extensible, performant, and developer-friendly. So the high-level idea of how we go about designing such a thing is that we start with the cryptography, choosing a proving system that is performant and has the right trade-offs between proof size and prover performance, among other things. And for this, we use Starks. And then the next thing we do is we create a virtual machine description. This uses an instruction set that is not a standard one like RISC-V, but rather something specific to us. And the benefit here is that the model of the virtual machine itself and the instruction set are easier to represent in zero-knowledge circuits than a standard instruction set might be. However, this creates the need to create compiler tooling to prevent developers from having to work in this unfamiliar environment themselves. So we want to be able to compile programs from something like C into our instruction set. From here, and these are the parts that are a little bit forward-looking, we want to use hardware acceleration ranging from GPUs to ASICs to really get the best possible performance. And we want to use formal verification for core components like especially the proof verifier and the constraint system itself. If you were at Justin Drake's talk earlier today, we see there's some exciting things coming up from the Ethereum world on both of these fronts. So the VM we can think of as having communication on two sides. On one side, it talks to the prover. The prover is an engine that creates the zero-knowledge proofs themselves. On the other end, it talks to the compiler, which translates ordinary programs into the instruction set. At both of these, there's opportunities for optimization. So the idea is that because zero-knowledge circuits are very different from ordinary electronic circuits, the design of an instruction set might look different. For example, in ordinary electronic circuits, it's important to have to use cache and registers as much as possible because accessing them is faster than accessing main memory due to the physical location on the chip. This, of course, has no meaning in the abstract world of zero-knowledge circuits. And so one of the things that we change is we get rid of registers. I'll say a little bit more about that in a second. And then to support this, we need to have compiler tooling that rewrites code that uses instructions that we don't want to include in our instruction set and replaces it with equivalent code that does. So our system we can think of as consisting of a set of chips modeled on how an actual processor works. So there's the main CPU module, a module for memory, a module for binary arithmetic, as well as some more specialized things like in range checker chip. So each of these is sort of an independent circuit that communicates with each other using the I/O of the circuit, as well as additional arguments to verify compatibility between them. So here's a schematic of what this looks like. Our memory is divided. This is a Harvard architecture. So main memory is separated from the memory, including the source code of the program, as well as a special tape for the input and output. These communicate using a series of buses, which are just the public I/O of the circuit in circuit language. Now here's some interesting choices. So the only registers that we support are two special purpose registers. One contains the program counter, so that's the address of the current instruction in memory. One contains the frame pointer, which is where the stack frame begins. We do not include any general purpose registers like an ordinary CPU has. for the reason that it's no more costly to work with main memory than it is to work with registers in our setting, and having registers requires us to have trace columns for each register. In the AIR programming model used by Starks, this creates a pretty heavy overhead for each register. So the way that we work with memory is that you can address it in two different ways, either relative to the frame pointer or using addresses. So instead of an instruction reading something from one of 32 registers like you have in RISC-V, you put everything in main memory and address it using offsets from the frame pointer. So this would include operands for an instruction, return address for function calls, that sort of thing. And like I said, it's a Harvard architecture. You can't address the program memory that's separated. So in some sense, we have a separation between stack and heap. Stack grows in one direction, heap grows in the other. I'm not going to say too much more about that. But yeah, so we can think of the software as consisting of three big parts. One is the execution engine, which runs the actual program and generates an execution trace. One is the prover, which takes the execution trace and turns it into a zero-knowledge proof using cryptography, and then the last is the verifier. This is the same setup that every VM has. One key thing about our design is that we use the baby bear finite field. This field is awesome because arithmetic in it looks very similar to ordinary 32-bit arithmetic. Reducing something modulo p for this p is a very fast operation in actual hardware. However, this field is too small to provide the requisite amount of cryptographic security, so when we do challenges, we have to draw them from a larger field. This is a degree 5 extension of this field given by adjoining a fifth root of 2. Nothing particularly special about the fifth root of 2 here, it's just some degree 5 extension of this finite field. They're all isomorphic. And then we use Starks, so the commitment scheme of interest is the Fry polynomial commitment scheme. However, we are looking at the possibility of using some new commitment schemes that came out this year, such as basefold. So the general way the operation works is we have one execution trace for each chip, so the memory, the arithmetic, the CPU. And then we encode these traces, which are vectors of scalars in this 32-bit field. We encode them as univariate polynomials using interpolation, the same idea that is used throughout ZK. Commit to these using Fry. And then the last bit, which is a little bit interesting, is to ensure compatibility between the I/O of the different chips so that the CPU has the same view of the information being exchanged between it and the memory chip as the memory chip does, because these are separate constraint systems. This uses a permutation argument, similar to the way that copy constraints work in Plonk. Then to get the actual proof, we plug these into the constraint equations. These are multivariate equations. This is the AIR constraint system, but plugging in a bunch of single variable polynomials, each constraint gives us a single variable polynomial, and then we combine these using random linear combination from a challenge alpha generated by hashing the everything committed to so far. Then finally, to show that this constraint vanishes on all of the points used to define the polynomials, we show that we know the quotient by the zero fire polynomial, which is the one that vanishes on the set of the domain. Okay, this is the same construction that's used in every Stark and broadly similar to the constructions used in other snarks as well. But we do this once for each of the chips. We get all the execution traces, and then only after all of that is done, we generate the traces for the permutation argument. One thing to note here is that all of our constraints have degree at most 3, which helps keep the cost down. Also, Starks only use hash functions, so we completely avoid the need for 256-bit fields, elliptic curves, and other expensive cryptographic operations. I already mentioned this, that this baby bear field, also known as the 31-bit Mersenne field, or Mersenne prime, has extremely good arithmetic. Here's a diagram of our compiler pipeline. So we use LLVM because it's something that enjoys a wide degree of support and has compilers from your favorite programming language, i.e. Rust. Okay, just dropped the pointer. Here's another schematic of this. So we see that we pass through a series of intermediate representations from the LLVM IR generated by the ordinary LLVM compiler. We then optimize this to end up with something that is instructions for our specialized Valida language. Something that we care about a lot with Valida is that we want everything to be very customizable. So you can go right now to our GitHub, download this, and spin up a VM with your favorite series of configuration choices. We want to be modular in sort of all aspects of the cryptography, from the choice of polynomial commitment scheme to even the arithmetization and stuff itself. Also, everything that we do is fully open source, Apache MIT licensed, so you can use it and do whatever you want with it. Finally, and this is what I'm going to say a little bit more about in my Accelerate talk tomorrow, but here's some numbers from running a basic Fibonacci program. And we see that we end up 933 times faster than RISC-0 running on the same program. So that's pretty good. Finally, click through. Here's an idea of what the developer interface might look like. I don't really have time to say more about that. But I wanted to make sure to mention our early access program. So you can use the Valida VM now, help us develop it. And also, we are hiring. So let us know if you're looking for a job. We're hiring for compiler engineers, cryptography engineers, contributors, as well as product people. Here's our contact. Lita XYZ is the company Twitter. My Telegram is TesseractIon, and Ventali's is Ventali08. And that's it. Thanks very much.